So last example, that the theory of commutative rings have no model companion. And this will be foolproof. So like before, the problem was with conjugacy classes. Here it is with nilpotent elements. So it's a bit like order degree of nilpotency, one may think. Okay, and also you see this doesn't appear in fields, this problem, because we don't have even zero divisors.
We wrote something like theory of fields had model companion, and we wrote ACF.
Uh-huh.
I mean, commutative rings also have ACF.
But they don't have.
They're not fields.
Huh?
But we wrote that fields have model companion, and we said it's algebraic closed fields.
Yes,
Theory
yes.
of algebraic closed fields. Isn't it the same here?
No, the problem is that, you look at extensions, and not all commutative rings have extensions which are fields. It has to be a domain. So the theory of commutative domains have the same model companion as fields. But if you allow zero divisors, then you are totally outside. Then you cannot get back to fields and no. But yes, you may have such a feeling, but not. And actually, these nilpotent elements will be problem. So let's say we have a ring and R in R. Okay, so I'm just recalling that R is nilpotent. For some n greater than 0. Okay, and now something which will be for you problem. So the following are equivalent. Purely algebraic thing. First, R is not nilpotent. So the thing is that not nilpotency can be witnessed by something in extensions, and this something is that there is a ring extension Rs and element in S such that it is non-zero idempotent, so such that S square is S. S is not zero, and what divides what? And R divides S. Of course, in big S. So this is connection with nilpotency of idempotency.
There exists an S in S, right?
Huh?
There exists an S in S.
Yes. And there is. So this is actually existential sentence. Okay, so how did I put it? We have, okay. I think you said So first is this est, and second is the one which witnesses dividing. So exists x, exists y, x equals x times x, and x is not 0, and r times y is x. This is saying that r divides x. Okay, so this is, and this I will call by phi xy, and also this r, which is a parameter, but it will change its role later. So this is quantifier 3. Okay, so just a comment that R is not nilpotent if and only if in some ring extension such a quantifier 3 formula has a solution. Okay, and this is something to be shown. One direction is easy, one is more difficult. But now, if R is existentially closed, and this element is not nilpotent, it must be already witnessed in R itself. So if R is EC, then this conditions is equivalent that something has solution in extension, but R is existentially closed, so it must have solution already here. So then R in R is not nilpotent if and only if this already holds in R. Yes, by this problem 4 and by being existentially closed. But that means that now if we call this so let this Z now play a role of R. Then we see that this is a formula which defines the set of not nilpotent elements. And this is something which is pretty strange, okay? Because like this nilpotency or not nilpotency, it shouldn't be definable because there is this thing, there is n. But by this and by existential closeness, it turns out to be definable. And this is the reason the things will go wrong. So, and then, then for all R in R, R is not nilpotent if and only if. So as I said, hence the set of non-nilpotent elements is definable in this EC ring R. Okay, and then again, to get a contradiction, we should apply compactness theorem. But to apply compactness theorem, we should have a theory. So that's why existence of model companion will give contradiction. Okay, so similarly, then also, so by this psi-z, so of course the set of nilpotent elements is definable by its negation. So now if we assume that theory of rings have model companion C, T, okay, and then we will reach contradiction. So now it will be this compactness theorem argument. So introduce new constant. And so it will basically be element which is nilpotent, but for each n, r to the n is not 0. And that will be contradiction. So new constant symbol C, new language, and new theory. So TC is this model companion. It is the statement, so this says C, okay, because models are existentially closed, so in such models, this sentence about C, it says that C is nilpotent. But then also the clear contradiction to it, that all powers are not 0. So we will show so now claim TC is finitely satisfiable. Okay, so we have to show that in any existentially closed ring there is a nilpotent element such that for okay, so in the proof, if we have some finite then we can take the largest n, which appears here. Okay, so basically T0 looks like T okay. So actually, any existentially closed ring can be a model of this T0. So let R a model of T, so R existentially closed ring. And again, you can find okay. So look at the extension Rx nilpotent, okay. Okay, this one. So here we have an element in this ring. It is true that there exists element such that x to the n is not 0, but x to the n plus 1 is 0. of course, X. So since R is existentially closed, the same is true here. Okay, and take this, so take, yes, to find the model, we have to find the realization of the C. This doesn't look, so take C, okay, R as such X. So then, of course, CR is nilpotent, because CR 2n plus 1 is 0, and CR 2n is not 0. So this R CR is a model of T0 as we wanted. Okay, so this becomes finitely satisfiable. So by compactness theorem, there is some other, okay, I don't know, S, C, okay, maybe CS model of TC, but now the CS is nilpotent, and for all n, CS to n is not 0, which is of course contradiction. Okay, so maybe it got a bit long, but I wanted to give this idea what could be reasons that model companion doesn't exist. And actually, as also Hodges writes in his book Model Theory, that it usually involves some substantial mathematics to show that model companion doesn't exist. I don't know how substantial, but in both cases there was some mathematical argument showing algebraic argument that there are reasons they shouldn't exist. So I think it's not, okay. It's never really easy to show that model companion does not exist. Okay, so last problem. So I finished these examples. Problem 5, which I was saying. So something in similar spirit. So show that the theory of non-algebraically, show that the class of non-algebraically closed fields is not elementary. Okay, so there is no L-ring theory T such that R such that models are exactly not algebraically or non-algebraically closed fields. Okay, this cannot be axiomatized. Okay, so now I finished this general introduction to model companion. Now we are talking about theories we are interested in. So we are interested in theories of actions So I hope at least to tell at the last lecture for a finite group what are the axioms of model companion of actions of this group's own fields. So it will not cover ACFA. ACFA was like model companion of actions of Z. One automorphism is action of Z. Here it's a different story, just finite group. Okay. And what is the language? So recall that we have.
Lecture notes you wrote that you're generalizing this action, right?
Yes. Okay. In lecture notes, I'm also covering the case of Z, because actually they're kind of axioms. Okay. But here I will go easier way and kind of describe these axioms using the properties of Galois groups, which actually cannot be done in the case of Z. So I will go purely algebraic way, in a way which cannot be done in the actions of Z. So okay. Somehow finite groups are easiest. There are two ways to approach these axioms. One is geometric, one is algebraic. For Z there is only geometric, but it's a long story. I may tell at the end. If we see these axioms, I may say why it's not enough, this kind of axioms for Z. Okay, hopefully in the last lecture. But now I just want to say what is the language, natural language. So I think it's a good analogy to look at the language of vector spaces or modules. So now we have a ring which is fixed. And kind of ring becomes a part of the language because we are talking about modules over this ring. So the language of our modules we have plus minus 0. If you want, you can think about vector spaces, but then one unary function symbol for each element in R. So this will be interpreted as scalar multiplication. So the language itself becomes very, very big as ring. Okay? Because the universe will be a modular vector field or vector space. Okay, so there is 1 plus, 0 minus, but then lots of scalar multiplication. Because for each element we consider scalar multiplication as one unary function. There are also, okay, but then it gets a nice theory. You could consider R as a part of the structure, but then it's something else like R times V to V. But this will be something like two-sorted, which I didn't talk about, two-sorted structure. So, and it has worse properties. But this is natural language for vector spaces or modules. So similarly for group actions, similarly as here, we fix a group. But now we are acting by group not on, but here, okay, module is like action of ring on a group, and here it's kind of opposite. We are acting by group on a ring or field. Okay, but so our language of actions of this fixed G on rings or fields, so the universe will be ring or field, and each element of G will be like scalar multiplication. Okay, so this X. So this, I just described what is the language to consider actions as first order structures. And just a name by G ring or G field we mean a ring or field with an action of G by automorphism. So such things we want to understand as models of some theory of this language, and then ask whether a model companion exists.
Basically, in the characteristic 0, you are looking
Any characteristic.
But yeah, maybe. So you are just trying to embed some groups into Galois groups, right?
Okay, that's another issue. If the group is finite, you may think like this. But if it's infinite, then definitely it's not a Galois group. Because then this, okay, it may be the fixed points, the extension is not algebraic usually.
The group is not that has to be finite, right?
Right now not, but soon it will be. Okay, but in this setup not. And I will state some general questions which are interesting actually if it's arbitrary group. So Galois is not a very good intuition here and actually confusing. Embed, but just in the automorphist group of the field. But this may be something crazy, like automorphist group of complex numbers. It has 2 to the continuum elements and basically anything, all permutations of the transcendent basis and even more, because it may, so you cannot say anything. At least, yeah. Okay, but now the theory. So GTF, the LG theory of G fields yeah, okay, so anybody can imagine how to write it in this language. So first we just write the theory of fields in language of okay, so this is the language of rings, of course. This was L rings. So this doesn't use this lambda g's, but now we want to express that the action is I think it's called mixed associativity. So it's also left action. Identity of the group acts as identity automorphism, and there should be field automorphism. Okay, I'm not really writing first order sentences, but I hope you believe they are first order sentences. So, okay, no, this is first order sentence. I compose two unary functions, that's okay. Okay, this saying for all x, lambda of x is x. And this as well for all xy, the axioms of being field automorphism. So all is expressible. Okay, one remark, maybe not. So it's natural not to take all elements. So maybe that you were referring to what I say in my notes, but just generator. So it's often natural to put only some generators of G to LG. So for example, if G is Z, then we don't take unary functions for all elements of N, because they are all just powers of 1. So it's enough to look at this one. And this corresponds to 1. Yes, so we considered field with one automorphism instead of considering with infinitely many and adding axioms that others are powers of the first one, because it would be not very reasonable. Okay, so I think I can just state the main question and finish. Question, or I don't know, it's not really our problem. So characterize G such that model companion exists. And to be honest, I don't think I will, that in my life I will notice such a characterization, but who knows, I may be surprised. It's kind of okay, it's even hard. So one could expect there should be some algebraic characterizations, as we did with Oslem for torsion abelian groups. There we get a bit, okay, maybe not very strange, but we didn't expect so. It appeared during working what is a good condition, but in general it's hard, there is no good guess even what it should be. So maybe examples. Okay, so if G equals Z, then it exists, but this is the first surprise when you start to think about it, that Kowalski showed if this is z square, that it doesn't. Kowalski? Huh?
What was the name of
Kowalski? Okay, so what is the actions of z times z? This corresponds to actions on fields by 2 commuting. Okay, so you already see that the groups are they are a bit different, but not that different, and the answer is totally different. If you don't add commutativity assumption, it still exists. If you consider 3 groups, it exists. But here it doesn't. Okay, so something, there could be some other reasons, but in general, when you just get a group, it's really hard to say what can be the answer. And here even the proof, because the other ones, when I was giving you proofs, the model companion doesn't exist, there was also a reason. But in this proof, probably Kowalski saw the reason because he found this proof. It's possible to follow, but somehow there is no really clear reason. Something happens, some Galois theoretic properties happen, and at the end you get that one number is both even and odd contradiction. But there is really nothing to grasp, at least we couldn't. I mean, we could change this proof to show for semi-direct product. There is one action of z by z, which is not trivial, that it also doesn't exist. But still, it was not really understanding what is the reason here. So it's a bit unintuitive. So our goal. So describe model companion of GTF. So it exists when G is finite. Then it has actually nice algebraic describe, so I will focus on algebraic description. And for this, we will need infinite Galois theory. So I think next week I will talk about infinite Galois theory. So sudden change of topic, kind of. Nothing about model theory. And then at the end, I would like to connect these two things to show how in terms of infinite Galois theory, you can actually describe, actually it's also used in the proof, but what are the axioms of model companion here. So it nicely comes together, these two things. So I think it's all. Thanks.